Here's the key for exam 2. And the first question is naming this aromatic compound, and we would probably treat it as a substituted phenol. And the OH would get carbon number 1, thus this is 2-methyl phenol. And if you wanted to use orthomethyl methyl phenol. And if you knew the common name of a methyl hydroxybenzene, which is cresol, you could call it orthocresol. Nobody answered that on the exam. I was not surprised, but that is the common name of a methyl phenol. Second one asks about aromaticity. So the first compound has 2 pi bonds and certainly 2 lone pairs, one of which could participate in resonance perhaps, or participate in the p orbital conjugation. However, this carbon right here is a CH2. It is SP3. Thus, we don't have a continuous p orbital. So this is non-aromatic. No continuous p orbitals. That's really all you need to say for that one. The second one is a 7-membered ring with 3 pi bonds in it plus this cation. And if that cation is sp2 plus p, which is the normal state for cations, we do have a continuous assortment of p orbitals. We have a ring, it could be planar, and we do have 6 pi electrons. So this one is aromatic. It satisfies all the criteria. On to number 15. This is a roadmap problem, so just fill in the boxes. The first step involves bromination of the benzene ring, and then somehow we get the methoxy on the end there. So the first answer, that's pretty straightforward. Not many people had trouble with that. That's great. So we got our bromine there. And now we need to substitute the bromine with OCH3. So you might just put CH3O-, and indeed that's what most students gave. But this is not a simple SN2 process. Remember that is because we are on, this carbon is sp2 hybridized. So you can't do an SN2 process here. We need to have a lot more intense reaction conditions, so heat is required in this step. This is simply elimination addition. So the strong base would remove a hydrogen, creating benzyne intermediate, and then the nucleophile could add. So if you didn't show heat, you lost a point in this case. Then we have 2 more boxes that are empty, and we're getting to this compound, which still has the methoxy, but we've somehow added a carboxylic acid to this position, and we are given the final reagent, sodium dichromate and acid and water, basically strong oxidizing conditions. This is a reaction from the aromatic chapter where we have a benzylic hydrogen at this position. We can oxidize that straight to the benzoic acid, And so we would start with any carbon group at that position. Methyl is probably the easiest one to install, and we don't lose any carbons when we oxidize it. But basically we take this methyl, strongly oxidizing conditions, turn it into the carboxylic acid. And thus getting a methyl there requires basically methyl chloride and aluminum trichloride. And we'll pretend that the ortho is favored in this case. It may not be, but since we showed you that we wanted ortho substitution, there's really nothing else to do here. Just put a methyl group on and then oxidize that benzylic position. The last step here was from the ether chapter. We had a methoxy. We wanted to change that into an OH. And if you remember that cleavage of ethers involves the formation of alkyl bromides, except when you have a phenyl ring on one side of the ether, and then you keep your OH. So this is a perfect example of that. HBr is all we needed here. We don't even need excess HBr because really only one half of the ether can turn into the alkyl bromide. The other half stays as the phenol, which is what we wanted. And then this step is one that we'll learn in chapter 21, carboxylic acids and their derivatives. So I put that in there for you because obviously we haven't learned that yet, but that's acylation of alcohols to form an ester functional group. I hope you recognize this question number 4 that was identical to the quiz. It involves a donating group, activating group, and an orthopara director, and it involves butyl chloride, and we're going to form the electrophile first. And there's a couple ways of showing this. Again, you can watch the video of quiz number 1 and you're going to see the same thing. We can do a rearrangement here to form the more stable secondary cation. Remember, a big part of Friedel-Crafts alkylation is that primary substrates will always rearrange to form the more stable cation, and that's going to be this guy. And then we can attack that cation. And if you used ortho or para, I didn't care. I prefer ortho, so that's what I'm going to use. And I put an extra bond there. I got to start over here. So you needed to show that rearranged R group, and then we need to show 3 additional resonance structures here. This should be old hat at this point. We can show the extra, the 4th most important resonance structure, puts the cation on the O, and then I can draw 2 arrows here to get the cation in the 3rd or 4th position. Those are my resonance structures. I still have the extra hydrogen there, and I did make AlCl4 minus, so that's what I'm going to use as my base to remove this hydrogen. I'll take the AlCl bond, remove the H, put the CH bond back into the ring to reform the aromatic ring, and there's my product. So I got the rearranged product in the ortho or the para position. Here's some better choice problems. The first one looks like we got the same product, we got the same set of reagents, just different order. So we could put nitro on first and then acylate, or we could put the acyl group on first and then nitrate. And we can recognize that both of these substituents are meta-directors. So in terms of the substitution of the product, they don't matter which order goes first. And so that's not going to be the answer. The answer, I think, comes from the fact that we recognize that the nitro group is a strongly deactivating group. Friedel-Crafts acylation or alkylation will not occur once we've strongly deactivated the ring. So we should put the ketone on first and then nitrate it. So let's just say here, Friedel-Crafts acylation won't occur with strongly or even moderately deactivated rings. Part B. Here we've got some, looks like Diels-Alder conditions, and we got the Diels-Alder product. The only difference here is we've got cis relationship between the substituents on the dienophile. Here we have trans relationship, and this is a trans dienophile, so we'd expect to make this stereoisomer not the top one. So we would circle the bottom one again, and we would say dienophile is trans, thus the product should have trans stereochemistry. And we can notify it just like that. And lastly, looks like we again have substitution on a ring, same 2 substituents going on in different orders, and we've got the same products here. And so we can observe that the bromine is orthopara. I got some people telling me that it was meta, and that was obviously not correct. So that didn't help your points earning in this particular problem. The acyl group is meta, and so in order to get the meta relationship, we better put the acyl group on first, otherwise the bromine will direct to the para position. So basically the top one is correct, and we can say here Br is OP director, would not produce this isomer. Next page, predict the product. So we should observe in this case that there's a delta minus there due to resonance, there's a delta plus there due to resonance. So if I'm going to redraw these, I'm just going to flip the diene around, make some new bonds there. And this is a trans dienophile, so I need trans right there. and we could make the other enantiomer as well. So some students forgot to include the carbonyl here. That made me a little confused as to what product you were looking at. Some people put the carbonyl on the other side away from the OCH3, so they didn't assess it this way. Those were the common errors right there. B has a leaving group and strong base, strong nucleophile, and heat. So most likely we're going to form this intermediate, which can then react with NaOH and produce, sorry, there should be a methyl there, produce this. A lot of students lost credit because they did not draw the other isomer, the ortho and the meta isomer, and that's because we could attack at this carbon, which gives us the meta isomer, or we could attack at this carbon, which gives us the ortho isomer. Just because the chlorine is ortho to the methyl doesn't mean the product is only going to be the ortho isomer. So you need to think a little bit about the mechanism in this case. For part C, we need to assess two different rings here. We're going to add chlorine, obviously, to the ring. This ring is deactivated. This ring is activated. So we're going to react with the activated ring first in the ortho-para position. Para is already occupied, so we need to put a chlorine in the ortho position. That was pretty straightforward. I can't think of any common errors. That would be the desired product. For D, we are simply adding a bromine to this position, and that is just NBS. So if you answered Br2 and FeBr3, that was not correct. NBS will brominate the benzylic position. Br2, FeBr3 will brominate on the ring. Part E is a nucleophilic aromatic substitution. We have a good nucleophile right here. We've got a good electron withdrawing group, ortho or para, to our leaving group, and so we can do a nucleophilic aromatic substitution, and we just substitute the bromine for the OH. F is your standard electrophilic aromatic substitution, and if you recognize this oxygen as a donating group, it can donate into the ring, making it an ortho-para director, and that would be the product for F. And last, we have G, sodium, ammonia, and methanol. This is the Birch reaction. This is an electron donating group, so we want to make sure that we don't reduce that carbon, because that would involve an anion forming there, which is less stable when it's next to an electron donating group. So that would be the reduced product for the Birch reduction. Next mechanism. Here is a diene reacting with HCl under what we think are thermodynamic conditions. So we need to show probably the 1,4 product. So the first step, of course, is just protonation. And we're going to form the most stable cation. That's going to be this tertiary cation that has some resonance. There's the H we added. You don't need to draw that if you don't want to, but I'll put it in just for completeness sake. We do have one resonance structure here. And now our chlorine, which we formed from losing the H off of HCl, can attack the cation, forming this product. And in reality, it probably is the both enantiomers, because we're made a new stereocenter there. I actually didn't take that into account during the grading, but that would be a more complete answer. So this is the product we're looking for. Some students drew the 1,2 addition and labeled it minor. That's fine, as long as you showed me the 1,4 as the major product. Then we had the synthesis question. It was interesting that everybody chose that one. No one chose the first one. If we think about the first one, this is a diol. We know how to make diols. We just need an alkene right here and OSO4, as we learned from chapter 9. So there's my alkene. Everything else remains the same. And now we have a bit of a clue as to what the heck is going on here. This is a 6-membered ring. It's a cyclohexene. We've got an electron withdrawing group hanging off of that 6-membered ring. This is probably a Diels-Alder product where we just made this bond and this bond. There's the diene. There's the dienophile. Now, it said we could use anything we wanted to, but we had to start with this thing. Can I turn this into either of the diene or dienophile? And let's see, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I have the same number of carbons. All I really need to do is reduce my alkyne to an alkene. H2, Lindlar's catalyst will do that for me. I think I have an extra D there. Hopefully you'll forgive the poor spelling. So this is a three-step process. We form the diene with our first step, we bring in the dienophile in the second step and do a Diels-Alder, and then we react OSO4 with the resulting alkene from the cyclohexane that's formed in the Diels-Alder. Okay, nobody liked that one. I did, but that's not the problem, not the point. Most people chose benzene to make this di-substituted benzene. We observe a meta-relationship. This is an ortho-para-director, and this alkyl group is also an ortho-para-director. So at some point we needed a meta-director on this ring. The chlorine was not the meta-director, but remember that alcohols are very familiar to us, and we can think about them as being the same as a carbonyl. So if we had a carbonyl in that position, there is our meta-director. So I can use that carbonyl to add the chlorine in the meta position. And I just need to add that ketone to benzene. And of course that is pretty straightforward. We've already done that a few times in this exam. And that's all there was to that. Some students tried to use a Grignard to make this alcohol, and in some cases it worked just fine, so I gave them credit for that. It probably took maybe a few extra steps. Other students really had trouble reducing this ketone to an alcohol. A lot of students wanted to use PCC or the Swern or simply NaOH or H2SO4. None of those made any sense. We are reducing, so we need a hydride source. NaBH4 or lithium aluminum hydride would work just fine in this case. On to question 9, and since I cannot display 2 pages at once, I'm going to just focus on this data, and I'll read off the questions from page 5 in the exam and answer them on this page. So let's see here. We have the formula is C12H14O2. So the first question is calculate the HDI, 12 times 2 plus 2 minus 14, all divided by 2. 12 times 2 is 24, plus 2 is 26, minus 14 is 12, divided by 2, 6. That was worth 2 points on this page. So the HDI is 6. The second question asks about the IR data. What does the IR data tell you? This is very indicative of a H on an alkene, maybe an aromatic ring. This is indicative of an H on an SP3 type carbon. Not very informative, but useful. This, if you look on the IR data chart, is indicative of an H on an aldehyde. So we know we have an aldehyde. We know we have an H on an alkene. Maybe it's a ring, maybe not. And we know we have just standard hydrocarbons. I'm not even going to write that out. And at 1725, we know we have some sort of ketone or aldehyde. We already saw the aldehyde evidence with this number, but it's nice to have that there. And then we're missing, we said something about 2200 to 3600 and 3200 to 3600. And there was nothing at those ranges. So that tells us there are no OH, no carboxylic acid. So that's good to know. Most people recognize that. So that was worth 3 points if you would identify those 3 structures. The next question was how many chemically unique carbons are present in the molecule? We need to look at the carbon NMR spectrum. That's right here. We just need to count the lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there were 10 chemically unique carbons, and that is out of 12, so we know we have some degree of symmetry here. And then the next part of that was how many carbonyls are in the molecule. Well, we can tell that from the carbon NMR as well, because carbonyls appear at 150 to 200. We've got 2 peaks right here, right around 200. So there are 2 CO double bonds, and they are different from each other because we see that they are different peaks. Okay, so the next question is, what do you conclude based on the H1 NMR signal at 965 ppm? That would be this one. And if you look on your NMR data table, protons in the 9 to 10 range are aldehyde protons. So that is probably an aldehyde proton. We already expected an aldehyde proton based on the IR data. And this is a triplet. You'll notice it is a triplet. So that tells me that there is a CH2 next to the aldehyde. That gives me some information about the environment of the aldehyde. There is a CH2 right there. So let me make my 2 a little more clear. That's what I get for part D of question 9. There is an aldehyde with a CH2. If you didn't show me the CH2, you got 2 out of 3 points. If you showed me that CH2, you got all 3 points. Question E, what can you conclude from the proton peaks at 7.2 and 7.9 ppm? That's these two. From 6.5 to 8 is basically the aromatic region. We've got two hydrogen peaks. They look kind of like doublets. This implies a para-substituted ring. So really all I wanted you to draw was this ring. Some students drew a ring without the para-substitution. That was worth 2 out of 3. Some students drew alkenes or some other weird thing. That was maybe worth a point. But really we wanted to see that it was a para-substituted ring because of course we have symmetry now through those X groups. And then across the ring, this hydrogen is the same as this hydrogen, and this hydrogen is the same as that hydrogen. So that's where our symmetry comes from. Gives us two equal in integration doublets. Question F, what can you conclude from the peaks at 1.85, 2.55, and 2.75 ppm? A lot of students missed or forgot the fact that these all integrated to 2 hydrogens. So if you try to tell me that this at 2.5 is equal to a methyl next to an ester, that was not correct. How can a methyl integrate to only 2 hydrogens? This is the methyl signal in our NMR spectrum. We see that it is 3 hydrogens right here. So this is a methyl ketone actually, because at 2.2, it's exactly where we'd expect a methyl ketone. So I'm going to make a note of that. I didn't ask you about that on this spectrum, but that's what we conclude from that 3 hydrogen signal. So going back to these 3 signals, they're all CH2s. Most likely, they are all involved with each other in some way because we've already taken into account these aromatic signals. This methyl signal obviously does not couple with anything, and the aldehyde perhaps might couple with one of those CH2s, so that's quite possible. And these are near some electron withdrawing group, maybe the carbonyl, maybe the ring. This one is probably in the middle of a chain of CH2s because it's not as shifted. So let's make a chain here, and let's call this one right there. That is a pentet, and we'd expect that if it had 4 nearest neighbors. So we have 2 different signals here. So this is not a symmetrical chain, so maybe I'm going to erase one of these X's here, and maybe we'll come up with something else in a second. So let's think about this CH2 is clearly next to another CH2, and it would be maybe this CH2 if X does not have any hydrogens on it, and that could be maybe the ring. Maybe X is the ring. And then I'm going to look at this CH2 being the quartet. Now that quartet is interesting because these 2 hydrogens are already next to 2 hydrogens, so that might make them a triplet. But this is a quartet, so there's 1 additional hydrogen that they're next to, and that has to be right here. And the most likely candidate for that is the aldehyde, right? Because we already know that the aldehyde is next to 2 hydrogens, it's next to a CH2. So if I put the aldehyde on the end of this chain, it's next to a CH2. So this would be the part structure I was looking for full credit for part F. If you just drew a line of 3 CH2s, you got 2 out of 3 points. And then lastly, draw a reasonable structure that fits all of the spectral information and the chemical data. So, or the chemical formula, I should say. So here's my para-substituted ring. I also know that I have a methyl ketone, and I have this aldehyde on the end of a 4-carbon chain. I think that's really all I have left, right? So here's 4 carbons, here's 2 more, that's 6, and here's 4 more, 6 more, so that's 12, and my formula is 12, so I got all the carbons accounted for. I have 2 attachment points on this para-substituted ring. I have one attachment point on this methyl ketone, one attachment point on this 4-carbon chain. Let's just put them on there. And that's it. I know the aldehyde has to be on the chain and not directly attached to the ring because the aldehyde is coupled to 2 hydrogens next to it. If the aldehyde were right here, it would be a single peak. It would not be coupled, it would not be split into a triplet because it would not have any nearest neighbors. So this is the only way to match the formula and the spectral data. I do want to point out that well over half the class did not even match the formula. And I understand this might have been the last question you worked on. Maybe you were in a hurry. That's cool. I understand that. But you didn't get any partial credit if you didn't match the formula. If you matched the formula, you at least got 1 point out of 4 for part G, the actual final structure. So just keep that in mind in the future. If you don't match the formula, you're not going to get a lot of points, at least on the final structure solving question. Some students got 2 or 3 points depending on how varied their structure was, but this is what we're looking for. There was one student who did solve it. All right, the bonus. Let's talk about that, and then we'll be done with this exam. So we're asked to explain this outcome. This nitrogen here has a lone pair. It is obviously an ortho-para director, and this first reaction, bromine and iron tribromide, proceeds just as we'd expect. No big deal at all. However, when we mix these 2 acids with our dimethyl we get the meta director. How does that work? How do we turn, some students said, well, nitro is a meta director, so it'll go meta. But there's no nitro here to direct this nitro group meta. So the fact that the substituent is a meta director has no bearing on the answer here. Somehow, the dimethyl was turned into a meta directing substituent, at least temporarily, in order to put the nitro group on meta. A few students recognize that nitrogens with lone pairs are good bases, and so the substrate in this case is actually that molecule, protonated dimethyl. This is now a meta director. Remember that we've removed the lone pair from the equation. We now have a positive charge next to the ring, so it's less favorable to form positive charges here. Therefore, we would put substituents at the meta position so that our intermediates, our resonance structures, do not form that positive charge. So let's see, when mixed with acid, dimethyl becomes protonated, and that makes it a meta director. And that was all you needed to do for this question. You can look at it in the book. It is question 1983.